Hello, everyone, and welcome to the CSCAN InfoCAN sponsored CSearch conference. CSCAN InfoCAN is a professional organization for Canadian computer scientists, and we are extremely delighted to have with us today Professor Yoshua Bengio. Professor Bengio is a Canada CIFAR AI Chair at Université de Montréal and MILA, which is the Quebec AI Institute. He is one of the pioneers of deep learning, which is the main branch of machine learning and has really taken both the academic and industrial world by storm. And in fact, he has recently received the ACM Turing Award for his pioneering research in deep learning. And we are delighted to hear today about his work and his directions for future work.
What I see as challenges for deep learning and where I want to go with my group, where I'm trying to steer research towards getting us closer to human level AI. And then the last third would be even more serious stuff about our responsibility as computer scientists and AI researchers and engineers with respect to social impact and some of the questions I want to share with you about this topic. Well, I wish I could speak for much longer, but here we are. So let me share my screen. Yeah, so a lot of the technical stuff I'll talk about comes from a group of 4 or 5 papers with a number of overlapping authors that I want to thank here. And let me start by telling you a little bit about how I got into this field of deep learning or neural nets. When I was a grad student, I didn't really know what I wanted to do, and I was reading a lot of papers and kind of searching for exciting stuff. I was a big fan of science fiction already. And at some point, I started reading these neural net papers in the mid-'80s. And I just got like so excited about these papers. I guess I had always been interested in understanding intelligence. And it turned out there's this field of research which is at the intersection of computer science and brain sciences that try to understand and uncover, if they exist, some sort of general principles that would give rise to intelligence. The intelligence that we have, animals' intelligence, and of course help us build intelligent machines. So the idea would be, is there something like the laws of physics for intelligence, something that we can understand, we can write equations for? Now, it doesn't mean that building intelligent machines would be necessarily easy, in the same way that even if we have the laws of physics, we can't easily predict everything that's going to happen because it's too complex, right? So we can't always predict the result of experiments, but somehow we can understand the principle behind the results. So that's how I got started, and I was so passionate about it, I continue doing it. So what is this neural net approach to AI, right? AI is about building intelligent machines, and in order to take intelligent decisions, you need some sort of knowledge about the world. And when I say knowledge, I don't necessarily mean the kind of knowledge we put in a book. In fact, neural nets are a lot about the kind of knowledge you don't put in a book. And then later in my presentation, I'll talk about knowledge we do put in a book and we'd like to also put in neural nets. So the kind of knowledge we put in a book are things we can communicate with natural language. But there are a lot of things your brain does, which is like perception, which isn't like this. And it's hard for humans to have that self-knowledge of like, how do I recognize objects and images? And engineers and scientists have been trying to write programs that would like recognize objects and images for decades. And it's hard. Your brain does it like this in about 200 milliseconds. But how does it do it? It's not obvious. And so that field of research in AI is trying to get clues from the brain and cognitive science to suggest forms of computation that may be useful for building intelligent machines. And neural nets, so that's the brain-inspired part. And in particular, one of the building principles is that these neural nets are obtained by composing fairly simple adaptive computational units corresponding roughly to neurons. You've got a huge number of them in the brain, like 100 billion, and somehow they send each other signals. And so information is represented in a way that's very different from in your normal programs. You don't have symbols. You have what we call distributed representation. So an object is represented by a pattern of activation. And I worked a lot on that in the context of natural language a couple of decades ago. It has really had a big impact in the field of natural language processing, which is weird because language, you'd think, is maybe the part of AI that should be strong on symbols, but really it turns out that even if, as Geoff Hinton keeps saying, for example, machine translation, if symbols come in, symbols come out, but the stuff in the middle, it doesn't have to be symbols, and in your brain it isn't. In the current state of the art machine translation system, actually coming out of some of the work we did about 6 years ago in my group, it doesn't use symbols either. It used special kind of neural nets with attention that I'll come back to. Going back to this physics analogy, so as we try to abstract out what machine learning does, in particular, neural nets, but machine learning in general, a lot of machine learning can be boiled down to a very simple recipe where a system that instead of being programmed is going to learn is going to do it by defining three things, by defining an objective or reward function. So what is it that the system wants to optimize? Then how you're going to optimize it. So it's an optimization method, or in the brain, a learning rule, like how do the synapses change in neurons? And then the third element is, what is the set of functions? What is the architecture of the neural net, the parameterization of the system that is going to change as you learn? So these three ingredients, basically, once you put them together, bang, you get a system that can learn. And a lot of algorithms, learning algorithms, can be defined like this. And many of them follow the idea of end-to-end learning. Like you may have many pieces in the system, but somehow they collaborate together so that they optimize this joint objective. Okay, so that was the part about history. Now let's look a bit forward. What are the missing pieces for getting closer to human level intelligence? Yeah, so there are probably a lot of directions, but one thing that has caught my eye in the last few years is that learning theory, like the math behind why those learning procedures work, is based on assumptions about the examples, the data that the machines are learning from. And then there's like a really core assumption that's the idea that the examples are independent and coming from the same distribution. But in real life, it's never like this. I started noticing this in the 90s when I worked on time series. They're non-stationary, like the distribution of data that a learner sees in their lifetime keeps changing. And if you're like Doina working on reinforcement learning and you're thinking about agents in the world, it's even more the case, right? When we train a machine in the lab, we can cheat and pretend that the data comes from the same distribution by shuffling the examples. So now they look like they're all from the same distribution, right? But in real life, it's never like this. And it's a problem because when we deploy a machine learning system in the field, and this is also something I've been involved with in industry and in all kinds of applications, what you find typically is the systems don't work as well as they did in the lab. Kind of bad news, right? And that's because they were trained on some distribution that, the data was collected on some distribution, but then really you use them in a different setting. You train from data coming from a country and you test in a different country, and it doesn't work as well. So this is something that a lot of people are interested in these days, but it's a fairly new subject in machine learning, and I would say it's one of the most important ones. So how do we deal with that? Because it's kind of funny, like, why would you expect that a system that's been trained on a particular kind of problem, of data, of questions that you ask the system, why would it work on different things, right? If I teach you how to drive your bike, why would you, be able to drive a car? And the funny thing is, humans are really good at that. We can learn new tasks very quickly, and that's connected to our ability to deal with changes in distribution. So this ability to represent knowledge in a way that we can break it down into small pieces and then reuse those pieces in new ways, I think, is at the heart of, the solution to this problem of non-IID, non-stationary data, or changes in distribution. So that's one aspect. Another aspect I'll talk about today is causality, which is really exciting. Again, new way of thinking in machine learning that has a long history in other disciplines, but it's really new in our field. Okay, and so let me focus now on the the notion of reusing pieces. So as I said, you look at the picture on the bottom there, and you can understand, what's going on because the stuff on the top here, and your brain is able to kind of combine the pieces of knowledge know. And what's exciting is that your brain is able to do that even though you've never seen anything like the image. And we do that all the time with natural language, and linguists have been studying this. They call this systematic generalization or systematicity. For example, I can tell you a science fiction story, and of course, it doesn't correspond to any of your personal experience, but you can understand the story. You can drive in a new country you've never been, where the traffic laws are different, and somebody tells you, more or less what is the difference, like you have to drive on the left side or instead of the right side. It's a struggle, but you're able to do it. And if we look at how humans do this, when they're faced with a new situation, like driving in a new country, it's like in the picture here, you need to do it consciously. Like, you need to pay attention to what is going on. If somebody's talking to you at the same time, please let me. I need to focus here. So there's something in the way that your brain is handling these changes in distribution that we really would like to understand better, and that is inspiring these new approaches that I'm gonna give you a gist of. Yeah, and then why we're trying to solve this problem, because current deep learning, current neural nets are not doing that great. Many studies have shown that when you change the distribution, they sort of fail, not completely, but it could be pretty bad. So clearly, we want to work on this. So I mentioned the notion of reuse of pieces, and I gave you an example already. It's connected to a notion that's central in computer science. It's compositionality, right? I mean, that's the bread and butter of algorithms and computer science. We already have some forms of compositionality, like reuse of pieces, that are inherent in the standard kinds of neural nets, and I've studied this in the past, and deep learning in particular. But somehow we need more forms of compositionality inside sort of the next generation of deep learning that I'm hoping to build. Yeah, so going back to humans, we're somehow able to do this. And by the way, like, one of the interesting questions you can ask yourself, like, what's the point of being conscious? And one of the side effects of our ability to handle things consciously is this ability to learn new things quickly, to solve new problems, to plan on the fly, to recompose pieces of knowledge, reason, and so on. So this is something that, of course, in classical AI, symbolic AI and search-based approaches, that production systems, that has been explored a lot in the 60s, 70s, 80s, and so on. But it hasn't really made its way in a lot of modern machine learning applications, and machine learning needs somehow to incorporate this kind of explicit data knowledge manipulation, maybe inspired by how humans do it. So one of the interesting sources of inspiration is this book I read a few years ago from Daniel Kahneman, Thinking Fast and Slow. It's a very easy to read book, and it really tells us something interesting about this human ability of doing things consciously. It turns out that there are really two different kinds of tasks that your brain is good at. There's the system one tasks and the system two tasks. The system one tasks are the things you can do without even being conscious of doing it. I mentioned perception, but a lot of things that you can do without having to think. Like if you drive in a place that you don't need to pay a lot of attention. Um, uh, the whole thing is happening in a very parallel way. You use knowledge that you don't have access to explicitly, as I mentioned, like in perception. Whereas, so if you're recognizing a cat in a picture, that's system one, for the most part. And then system two, if I ask you to solve, to add 33 and 34, you probably need to manipulate a few symbols in your mind, right? And it's going to be slower. It's going to be sequential. It's going to be logical, and it's something you can explain to other people. And so you can write a program. This is how we program. This is the part that we would like to have neural nets that are able to do these things as well. Okay. So that's connected to a big philosophical question about knowledge. In the old days of AI, when I started doing my grad studies, we thought about knowledge as just explicit knowledge, the stuff we put in books, the stuff we put in programs. But all of the work we've done in machine learning and neural nets tells us that there's all of this knowledge I mentioned that we don't have access to. Like, how do we recognize objects, or even do a lot of more complex tasks? But and so there's like system one knowledge and there's system two knowledge. It's not exactly nicely cut like this, but roughly there is information about the world that we can verbalize, and there's information that is harder to verbalize. There's also information that we can verbalize, but we put in system one so it can be more efficiently computed. So one interesting hypothesis that I've been talking about now for a year or two is that one reason why we have these two parts, system one and system two, and then the conscious part and the unconscious part, maybe because there are aspects of the world which can be easily reduced to the verbalizable form, and aspects that are not easy to reduce to the verbalizable form. And why would it be advantageous? But because the verbalizable knowledge, the explicit knowledge, actually is very constrained. If you think about it, it's the language channel is allows you to only say a few things at a time and manipulate just a few variables at a time. Whereas the unconscious processing can handle a video and tons of data all in parallel. But the statistical dependencies between those variables may not be easily reducible to something we can verbalize in a few sentences. And so there may be aspects of the world that satisfy some assumptions, some priors, as we say in machine learning. And if we can, somehow take advantage of those priors, then in principle, we could generalize better. So that's the thing about machine learning, right? So learning is never completely ab initio. You exploit assumptions about the data distribution in some forms. And if the brain evolution has found that there are some aspects of the world that can be advantageously treated in a different way because they satisfy some of these constraints, then maybe that helps us generalize. All right, I'm going very slowly. I'm not going to go through this, but I'm going to give you some examples of some of the work we've been doing in that direction. So one of the ideas that I started in 2017, but that is now in a lot of current papers, is connected to what I just talked about. So the idea that this system two conscious verbalizable knowledge has a special form to its distribution. So for representing joint distributions between lots of random variables, there are many ways we can do that in machine learning. or probabilistic modeling. And the particular constraint that I talked about for verbalizable knowledge can be essentially said in that the dependency as follows: the dependencies between the variables, those high-level variables like words and sentences, the dependencies have a sparse form, meaning that, think of it like each sentence, which is like a statement about the world, like if I drop the ball, it will fall on the ground. Each sentence like this involves very few variables. That's it, right? So not everything is connected to everything. Like each variable is involved in a specific mechanism or causal dependency with other variables, and that causal structure involves very few elements. Otherwise, we couldn't use language to express this. It wouldn't be convenient. So the fact that we're able to say all these things, to make those very strong predictions about the world using these sentences, tells us something about the probabilistic structure behind the high-level semantic variables that we manipulate consciously. So that's nice, but we don't get those semantic variables from raw data. Like our robot is going to see a video, right? It's going to see images. It's going to hear sounds. And so one of the thing we want is to transform the low-level data into these some kind of representation of these high-level semantic variables that we can then model with this sparse structure and causal structure. So this is the kind of thing we're trying to do. Until recently, a lot of deep learning has been just focusing on that encoder mapping the raw data to some high-level variables, but where you use supervised learning. You tell the system, oh, there's a cat in the image, and so tell me that there's a cat. You output, there's a unit that says cat. But really, we haven't done that much work in figuring out how these different variables, these different high-level variables are related to each other so that the system can figure out that, cats behave in particular ways that maybe have some similarities with dogs, but are different in other ways, so that you can predict what will happen in an efficient way. So we're trying to put these two things together. We need to find representations that have the property that the output of these, we call them encoders, they encode raw data into high-level representations. The output of these encoders correspond to these high-level causal or semantic variables. And so that's kind of the research program. And one of the properties that's really cool and goes back to my initial question about changes in the world, changes in the distribution, non-stationarities, things change. You were trained on some data and suddenly something happens. It's not the same thing. So that the way that the world changes out there, sometimes, not always, can be explained using sentences. Like I say, oh, somebody turned off the light. So there's one bit that changed in the world, but that's a bit at the high level. It's that switch was turned off, and so you need to learn those representations. But those representations now have a very special property that when there's a change in distribution, it's localized to just one of the variables or very few of the variables, and we should be able to exploit that. So we actually have several papers. We're trying to do this. I won't have the time to go into these papers, but just want to mention that these are some of the hot topics that we're exploring, because they could really help us make machine learning systems, AI systems that would be more robust. And one of the ingredients here is causality. Why? Because the way that causal science has developed and really thought about how to explain the world through causal structure is through the idea that precisely the interesting changes that we think about are when an agent, like a person or an animal, or eventually a robot, intervenes in the world, does something which changes one of these high-level variables. And you can see that if we are able, again, like to describe the change with a sentence, that it probably means that that property is preserved. And so if we can observe, it turns out that if we can observe these changes in distribution, we can make inferences about the structure of that graph. Because if we have the right structure, then the change will be localized. And if we don't have the right structure, it won't be. So this is some of the work we've done. Right, and yeah, I'm gonna skip. I always kind of take too much. Let me say a few words about attention, because that's also cool and kind of easy to understand, because we all have attention mechanisms that we are conscious of to some extent. We focus on some things. Maybe you're not focusing on what I'm saying right now. That happens. Your brain wanders. It's actually useful. Your brain wanders, but that's a different talk. So attention is something we didn't really do in machine learning until very recently. And I mentioned a few years ago, we worked on machine translation and it worked really well. And the key ingredient for the success of this was using attention mechanisms. So what it means is that operations in the neural net, instead of being static, like the connection between some piece of network, like, I don't know if you see my pointer, but going from this block of units into this block of units, there's always a connection, let's say. That's when you don't use attention mechanisms. And you might think that in the brain it's like this, but actually there are modulatory connections and multiplicative connections in the brain that suggest, and also lots of evidence that attention mechanisms modulate the interactions between different parts of your brain, that suggests that it's actually a lot more dynamic. So attention mechanisms in your brain allow to route information dynamically in a different way each time, depending on the context. And usually attention is also competitive, right? So like you pay attention on one thing, that means you don't pay attention to lots of other things you could. So that sort of competition turns out to be interesting because it helps to decompose knowledge into smaller pieces that are independent of each other. So that's another theme that we've been exploring in my group. Modular neural networks that use attention to force a sort of separation of representations into pieces that are kind of independent of each other, and that at runtime, the attention mechanisms which gates these connections decides which pieces need to talk to which pieces. Now, there's also cool connections between attention and classical AI. And that it's really making the connection to the old question of having actual variables and having types and having names. Because the way that attention works is, at least the way that we implement it in neural nets nowadays, is in order to compute which block of units is going to talk to another block of units, these different blocks compete. And the way that they compete is they announce what we call a key, which is a pattern of activity that says, this is what I have to offer. And if that's a good match to what the guy on top wants to get, which is, we call a query, then that the one at the bottom that has the good match is winning. So those keys, they're like a kind of type, a kind of name for the information that is then propagated to the next guy. And so in a way, seep into these neural nets notions of types and names and indirection, because the guy can also receive the key. And so it not just, if you think about variables in programming, right? You have the values that are stored, but you have somehow like the pointer or the name. And that's maybe important as well, somehow, if you want to do this symbolic manipulation. So very interesting connections are arising. Yeah, I'm going to skip that. And now shift gear to the really serious stuff. And that is, what are we going to do with that technology? So first of all, at least the way that I see it, it's really important to not see AI like some sort of magic thing, as many people unfortunately see it now. The kind of machine learning systems we have right now are really dumb and far from, we are far from human level AI. But the tools that we have built, and it's going to be, even more the case in the future, are becoming very powerful. And you know what? Humans are tool builders. That's what we do. But the thing is, with technology, not just AI in general, we're building more and more powerful tools. Why is that? Why should we worry about this? Well, a more powerful tool can bring more positive social value. But think about weapons, right? So if you can build very powerful weapons, it's also more dangerous. Powerful tools can be used to increase one's wealth or power. Think about authoritarian governments. With the current tools of AI, they can watch over their people and lock in the power that they have in a way that was never possible in the past. So this power of the tools that we're building is something we have to be really mindful of. In a way, it comes in contradiction with what democracy is about, which is not having concentration of power, but having everyone be able to have a say in how we decide things. So I think there's a really interesting open question, which is, how do we organize our societies so that these powerful tools that we're bringing into the world will be governed by our collective needs rather than by the interests of a few people. And that means this is not just something for computer scientists to work on, right? This is like a social science, political science, economics, law. I mean, lots of things that many of us don't have expertise in. So we have to really work with those people in the social sciences and humanities, and they don't have our expertise, right? And so it's I think we where is it? Yeah, I don't know. Okay, so we have a responsibility to be part of those discussions, and I think it's really important that students, undergrad, grad, in computer science start realizing that because our work is deployed in the world, is giving a lot of power to those who use it, we really need to broaden our education to also understand these societal level questions. Otherwise, we're just going to be tools in the hands of people who exploit that power. So AI can be used for good in many ways. I've been involved in all of these things: medical applications, environmental applications, education, democratizing justice, humanitarian applications. It's really cool. All the good things we can do already with the current science of machine learning. But it could also be misused, as I said. And one of the questions I've been thinking about in the last couple of years is a lot of these collective decisions that we have to take about how to govern AI probably need to be taken at international level. So I'm thinking about things like, how do we coordinate these AI for social good applications at the level of the whole planet? Because maybe the problem is somewhere in a country in Africa, and the expert is somewhere in university here in Canada. And maybe the money for this project is going to come from a philanthropy in California, just as a typical example. So that's something we could make progress on. Another topic I want to mention is, that I'm thinking about these days is has to do with data. So there are lots of interesting social and political and economic questions around data that I could talk about. But because I've been involved recently in drug discovery projects for COVID-19, it helped me understand some of the issues in the field of drug discovery, especially as they pertain with using AI for these things. So right now, what's going on is a lot of the data that is being generated for drug discovery is kept secret in each company that produces those data, because that's how the current rules of the game are set up. It's not advantageous for companies to share their data. In fact, this pressure to keep things secret is even seeping into academia, and that's bad for the progress of science. And it's particularly a problem when the progress in drug discovery is going to be more and more driven by all that data. So if each lab, each company has to essentially redo the same things, it's going to be very inefficient. It's already very inefficient, but it's going to get worse compared to if we found a way, an incentive system that would allow companies and, of course, university labs to share information in a more open way. And that's a non-trivial question because the natural economic incentives are not in that direction. So yeah, so what I'm thinking about is that we already so we could maybe set up a kind of international funding organization for research in drug discovery, a little bit in the model of what we already do for funding academic research, but that would be open to also companies, especially startups, to participate in. And that would have similar kind of rules as we have in academia, that information and the knowledge and data has to be shared, but it would be, very strongly not just encouraged, but mandated. And that would make the research and development in this particular area much more efficient. So I know that this kind of thinking is moving away from a lot of people think, okay, this is how things work. This is this is how the industry works, and there's nothing that we can do about it. But I think as academics, we have a responsibility to brainstorm and to enter into a discussion with society about how society could be different, so we can build a better world. And that's the kind of thing I find really exciting. So yeah, my last slide. So I started this part of my talk by talking about the power of AI, or the power of technology and science in general. And I gave an example, weapons, right? So think about nuclear weapons. Right now, it's not easy to build a nuclear weapon, which is a great thing. But imagine it was easy. And with software, it's kind of easy, right? If I know the algorithm and I can use some money to buy the compute power, there are a lot of things I could do. And so a lot of our scientific progress is not going to be done on computers and in AI in particular. One may be concerned about how all of this power could be end up used in a bad way by people who just want to either increase their power or might just be like socially maladapted or crazy or something. So it's like if you had very powerful weapons and you allow any child to use those weapons, you could see that you could have problems. So I don't have an answer to this, but one part of it I think is you want to make sure that you have as few angry people on the planet as possible, right? So if there are people who suffer a lot and they get to know about these weapons, you can see how that could turn badly. And so I think as we build more powerful weapons on this planet, we can't think of just our little country anymore. We have to think of the whole planet. We have to make sure that every human is well-fed, well-educated, and healthy, that they can understand the dangers. They can understand that it's in their interest to make sure that other people are also doing well, or that power is going to blow up in our face. Thank you very much.
Thank you very much, Joshua, for the wonderful talk. We have quite a few questions in the chat. Would you like me to read them to you, or do you prefer to just go through yourself?
Yeah, if you have some questions that you have looked at and we can start with, I'll be happy because it's.
Yeah, sounds good. So Philippe Rivet is asking, what do you think the low-hanging fruit are within the next 5 to 10 years for combining deep learning systems with good old-fashioned AI symbolic methods to improve general?
Oh, I like that question. So I would say what not to do is to try to think like in software terms. Oh, we have PyTorch and we have some good old-fashioned AI, pieces of software, and we're gonna somehow find a way to like engineer them together. That is not gonna work. I don't think so. And so what is the low-hanging fruit is maybe not that low-hanging in the sense that some work involved. Because it's really two different ways of thinking. That's what I was trying to say, two different ways of doing things. And so it's more like, how do I put a square in a circle or something like this? So how do I put something like symbols and logic into the probabilistic, soft, differentiable machinery of neural nets? Now, it's not like we're starting from zero. People have been thinking about these questions now for a while, but I see that we're making a lot of progress now. And I would say the number one reason why I think we're now equipped to do it better than any time before is because we have built all of these nice software tools actually for deep learning based on attention mechanisms. In particular, transformers are like the prototypical architecture, neural net architecture that uses attention that's extremely successful. Now, I'm not saying we can just copy transformers, but some of the ideas there are, I think, can be played with in order to gradually move towards being able to do the things we used to do in classical AI, but maybe in a different style.
Great. Majid Babai is asking, I'm wondering how would it be possible to move towards a solution for some critical philosophical issues such as self-awareness, determinism, and free will using AI?
Oh, I like that question very much. I think AI is an amazing field if you are thinking about these questions, but you also have to talk to your colleagues in the other departments, like cognitive science and philosophy and so on. So personally, I found that the kind of question I've been kind of touching briefly today regarding consciousness, for example, they're connected to those things you mentioned, like self-awareness, free will, and so on. And I think, at least I feel that I have a better understanding of these questions now than I had, if you had asked me 10 years ago, I wouldn't say, wow, what is that? I don't know, free will. And yeah, so my view on this, like to be optimistic, I'm hoping that the AI work on consciousness, free will, and all that agency is going to help philosophy, is going to help even neuroscience and cognitive science. By one way to think about it is, we can propose hypotheses for these things. We can test those hypotheses by making sure they actually bring advantages to the learning agents that we, simulate in computers. And that can suggest tests of these hypotheses in real humans, especially with neuroscientists or cognitive scientists. So I think we can really make progress by synergy of these disciplines towards these hard philosophical questions.
Thank you. Darren Abramson is asking, do you think the spirit of openness, which has transformed AI research with open machine learning frameworks, will continue if research continues to be corporatized? What should governments do to ensure public access to algorithms that are often nurtured through AI winters?
Yeah, I love that question. I mean, it was kind of the theme of one of the things I talked about at the end. The success of the software industry in many areas is in great part due to open source, right? Where somehow there's all this code that is being written without an immediate profit motive. And I don't think we have the right economic incentives right now for this sort of thing to happen in a more structured way. To me, the answer is obvious, okay? whether it's for discovering molecules or for open source software. And these are things that are good for society. And so society has to pay for it. No, seriously. We already are paying for a lot of things like healthcare and education, at least in Canada. I think we pay for research in universities. So I think that it's not crazy to imagine that we have an incentive systems that go beyond the borders of universities, that gives rewards to people who do things like software, like discovering drugs, or generating data that could be useful for advancing knowledge. That we need to find reward system or incentive system that's going to come from some sort of public funding for these kinds of activities.
Farin Lavji is asking, is there currently a strategy for extrapolation in AI to combat problems like lack of diversity in data models, for example, in facial recognition?
A strategy. Yeah, there's a lot of interesting research being done to try to address this. So there are technical aspects to this. Like one thing I was involved with is trying to find representations that are insensitive to sensitive variables like race and gender and stuff like that. But unfortunately, those technical ways of thinking about the problem are not always matched with what is the actual social problem, like discrimination, racial discrimination, that is happening in society. And so again, that's an area where we strongly need collaboration between the people who understand those social issues, like discrimination, and the people who understand how to build AI systems and software and so on. Otherwise, you're going to build something, you're going to think, oh, I have a nice mathematical definition of what is fairness, but it may not be that useful after all. So again, collaboration, open your mind to other people, admit your lack of knowledge. We have to be humble. Like we are experts in our little area, and there's like all of these other areas of knowledge. We need to work with this humility to be able to make progress.
Michel Barbeau says Université de Montréal is strong in machine learning, but also in quantum computing. Are these two disciplines related, and possible connections to be made?
We used to be in the same corridor. But now the machine learning guys have moved to a different building at Mila to join forces with the McGill crowd doing machine learning. So it's kind of, I think there are potentially interesting connections. I don't think a lot has actually been done there. There's a lot of buzz because you have two buzzwords, AI and quantum computing, and everybody wants to put buzzwords together in one thing. So it's kind of cool to do these things, but it's actually harder to make progress on this. Like, for example, we don't know yet any quantum computing algorithms. In other words, algorithms you could run if you had a quantum computer that actually helps to make interesting machine learning really much more efficient. And so we need more research in that kind of thing. So that's one area. The other area that's maybe a lower hanging fruit is when you build quantum computers, you have all kinds of issues of interference and stuff in real physical devices. The quantum magic doesn't hold very long. And so machine learning can be used as a tool to help the building of quantum computers that are going to be more efficient in the way they can correct for these imperfections that are happening in the quantum computers.
David Boulanger is asking, what do you think about interpretable machine learning or explainable AI? Because the literature mainly seems to care about predictive accuracy, ignoring descriptive accuracy.
So a lot of what I talked about is aiming in the long run to build machine learning systems that can bridge the gap between the low-level stuff like images, where we're already kind of doing well, and the high-level stuff which we can verbalize about, but we're not there. Also, it's important to realize that, as I said at the beginning, a lot of the knowledge humans have is not verbalizable, meaning that if you ask somebody, why did you do this? They might come up with a story. It's usually just the tip of the iceberg, or it might be completely wrong. It's called rationalization. And that's why expert systems had trouble, because you would ask human experts, why did you do this? So we can code that in the computer. And they would tell a story, but then that story didn't work that great. I mean, it was incomplete at best or wrong sometimes. And so, explainability, maybe we shouldn't strive for more explainability from AI than what humans are able to explain. So we can explain how the systems learn, but explaining how they come to a conclusion is as hard as explaining, having a human explain how they come to a conclusion. So I think we will make progress. In the meantime, there are very simple things you can do to understand, to analyze the decisions of these systems. You can, for example, very easily pinpoint which part of the input they focus on. If it's a visual, then it's, you get a lot of interpretation out of this. But it's there's no like general recipe for interpretability from neural net systems.
We have a couple of questions on causality. One of them refers specifically to the do calculus of
Yes.
Pearl, and whether you think that could be integrated with deep learning.
Yeah, that's what I'm doing. Not just me, but
wonderful.
Yeah, no. So if you've read the book of Why from Yuda Pearl, it's a great introduction to the field. And the things I talked about of representing the causal structure at a high level is also about how the mental picture you have of the world in the computer or in your mind can change under some action. That's an intervention. So do calculus is, what would happen if I were to change the value of a variable in a way that is potentially independent of the normal way that that variable would take a value, and I kind of override and I say, oh, I'm going to do this. It's going to change something. And it's kind of, even though it's still the laws of physics, I'm kind of, an agent is a funny thing. It's like, pretend the world has its physics and you are like God and you can change something in the middle. That's what interventions are. Of course, you're also part of the world and physics, but it's one way to think about it, which we haven't incorporated really much in current machine learning, but there's a lot of current work, there's a lot of excitement around these kinds of questions. So I think we'll make nice progress in the next few years.
We're almost at time, so just a couple of questions. They're sort of high level. One is, what's the role
I'll try brief answers.
What's the role of neuroscience in studying AI?
Neuroscience?
Yeah. Can we take inspiration, for example, from neuroscience?
Yeah. So there's inspiration. I've talked about it. And of course, we have to be careful because inspiration from the 80s, these guys have continued to work since then. So we should really continue to get to know about how the brain works. But it's even more exciting to think also we can give back. So one of the things I've been working on is working on hypotheses about how brains might be implementing something like backprop, which is an open problem that people have been talking about for decades now, but is of really great interest for neuroscientists. So potentially our work can provide hypotheses that are mechanical hypotheses, like it can be tested in brains. So the synergy is really exciting. And with the work that I've talked about in more the cognition level, that also has a nice potential for synergies.
Somebody asks about the trade-off between using benchmarks where multiple algorithms can be compared versus solving real problems. and how
You need
do
both.
you
What can I
feel
say?
about that? Is the research community's attitude the right one?
It used to be that working on toy problems that are artificial was not well regarded, but it turns out that it's still very useful. And of course, in reinforcement learning, as Doina knows, it's particularly the case. At the end of the day, it's also good to confront yourself with the real world. If you're building a robot, roboticists know that there's no simulator that does it. You know, that encapsulates all of the complexity of the world. I think they play different roles, and so we need to have both of these things.
And the final question from somebody who is new to the topic of AI, are there any resources you would suggest to look at in order to get a better understanding of the current state of art in AI?
I did write a book a few years ago. It's called Deep Learning. That was 2016. That's 4 years ago. I think a lot of the ideas there are still good. Unfortunately, we're so busy writing papers in this field that very few people take the time to write books. So if you're interested in reinforcement learning, there is an amazing set of lectures by David Silver that I have found amazingly insightful. And there's a lot of material online. So for example, in terms of software, there's a lot of tutorials, a lot of blogs. And the great thing as well is now you can watch talks online, a lot of talks. So there's a lot that's kind of easier access than it used to be 20 years ago.
Thank you very much, Joshua, for the amazing presentation and for handling the questions. And thank you, everybody, for participating. I hope you have a really good rest of the conference. And yeah,
Thanks, Doina.
Rest of the day. Bye-bye.
Bye-bye.